video, we'll look over advanced data augmentation and deep learning techniques with TensorFlow, Keras, and FastAI. Over the next several segments, we'll walk through a series of Colab notebooks, each demonstrating a specific technique. Part 1, Data Augmentation and Generalization Techniques. Segment 1A, L1 and L2 Regularization. We import TensorFlow and Keras, then we start by creating a simple sequential model. In the first tense layer, we apply both L1 and L2 penalties using regularizers.L1 underscore L2. These regularizers help to prevent overfitting by constraining the weights during training. After constructing the model, we compile it with the Adam optimizer and a sparse capable cross entropy loss function. Finally, we call model summary to display the architecture and verify that the regularization is in place. Notice how the input shape is specified on the first layer. This defines the expected size of our flattened inputs. For example, a 28 into 28 image flattened into 784 length vector. Part 1b, dropout example. We focus on dropout, a technique used to randomly set a fraction of inputs to zero during training. This forces the network not to rely too heavily on any single input and helps generalize the model. We built a model with two dense layers, and after each dense layer, we insert a dropout layer with a dropout rate of 0.05. This means that during training, half of the neuron activations will be randomly set to zero. We again compile the model and display the summary. Notice how simple adding dropout is, just one extra layer, yet it can significantly improve the network's generalization. Segment 1C, early stopping. We introduce the concept of early stopping, that is a callback that stops training if the validation loss stops improving, which prevents overfitting and saves computational time. We simply instantiate the early stopping callback by specifying that it should monitor the validation loss and that it should wait for 3 epochs of no improvement before stopping. I also print a reminder message that shows how to integrate this callback within model fit. This technique is especially useful when you are not sure how many epochs are optimal. Part 1D, Monte Carlo Dropout. In this section, we demonstrate Monte Carlo dropout. Unlike the standard dropout, which is active only during training, Monte Carlo dropout forces dropout during inference. This can be used to get an ensemble of predictions which help us estimate uncertainty in our predictions. We subclass Keras model and define a custom model called MC dropout model. Note that in the call method, the dropout layer is explicitly forced to run even when the model is in inference mode by passing training is equals to true. After compiling and printing the model summary, we have our model ready for uncertainty estimation. Part 1E, Weight initialization. Weight initialization is crucial for efficient model training. In this snippet, we built a model where each tensor uses a different initializer. For example, HE normal, Glorot uniform, and Lucent normal. These different initializers are designed for different activation functions and network properties. After building and compiling the model, we print a summary to check the network architecture and initializers used. This example demonstrates how choosing the right initializer can impact convergence and performance. Part 1F, batch normalization. Batch normalization is a powerful tool that standardizes the inputs to a layer for each mini batch. This speeds up training and helps stabilize the learning process. In our model, we add a batch normalization layer after each dense layer. By normalizing the activations before passing them to the next layer, we can improve training stability and sometimes even the final performance of the model. This code snippet shows the integration of batch normalization in a very simple manner. As you can see, we have applied batch normalization layer after each dense layer. Custom segment 1G, custom dropout and custom regularization. Here we take a step further and create our own custom layers. First, we define a custom dropout layer by subclassing TF Keras layers layer. In our custom dropout, we manually generate a dropout mask using TensorFlow operations. Then we define a simple custom regularization function that penalizes the absolute sum of weights. Next, we build a model that employs both our custom dropout and custom regularizer. This example shows how we can easily extend TensorFlow's base class to implement our own ideas. This is the custom dropout layer. Part 1H, callbacks and TensorBoard. We set up a TensorBoard callback, which is a powerful visualization tool that allows us to track training metrics, histogram of weights, and more in real time. We first define a logging directory and then instantiate the TensorBoard callback, setting histogram frequency to 1, meaning that weight histograms are computed after every epoch. Finally, a print statement reminds us how to use this callback. Integrating TensorBoard is as simple as adding the callback to our training process. Step 1I Keras Tuner. Keras Tuner allows for efficient hyperparameter search in our models. In this example, we first install and import our Keras Tuner and then we define a function build model that receives hyperparameters. Inside the functions, we create a model with a dense layer and use hyperparameters for the number of units, dropout rate, and learning rate. We then compile the model and finally we create a Keras Tuner instance with a random search strategy. The printed message reminds us to start tuning. We would call tuner search with our training and validation data. This is a great start for hyperparameter tuning. Segment 1J Keras CV data augmentation. We explore Keras CV for advanced image augmentation. After installing and importing Keras CV, we build a sequential augmentation pipeline that includes random horizontal flips, rotation, and zoom. This pipeline can be applied to an image tensor to generate augmented versions of an image. The example outlines how simple it is to set up a robust augmentation strategy with Keras CV. Here we create the data augmentation pipeline, and this is the example usage. Next segment, data augmentation for multiple modalities. First, we use TensorFlow's image data generator to augment images. This generator applies random transformations such as rotation, shift, zoom, and horizontal flips. Next, we demonstrate the text augmentation using the NLPOG library. In this, we perform a synonym replacement augmentation on a sample sentence. Both examples illustrate how we can diversify our training data for improved generalization, whether working with images or text. Here we can see the original text and the augmented text. Finally, FastAI data augmentation. We leverage FastAI's powerful data augmentation capabilities. We use FastAI's UNTAR data to download a sample dataset and then create image data loaders object for that folder. Note that we use random splitting valid underscore PCB since the folder structure might not have predefined training or validation folders. We also use item TFMS to resize our images and batch TFMS to apply augmentation and transformations. The code then calls DLS show batch to display a grid of augmented images. FastAI simplifies many of these tasks, which is great for rapid prototyping. And part 2, that is advanced Keras deep learning constructs. The first part is custom learning rate scheduler. In this first advanced segment, we implement a custom learning rate scheduler. The function custom LR schedule defines how the learning rate changes over epochs. For the first 5 epochs, it remains constant, then it decays exponentially. We then instantiate the learning rate scheduler callback with this function. This callback can be passed to model fit during training to adjust the learning rate dynamically, which is an important technique for accelerating convergence. Second, custom dropout, MC alpha dropout example. Here we build a custom dropout layer called MC alpha dropout. This layer subclasses TF Keras layers layer and behave much like the standard dropout during training. The key difference is that it is used to implement Monte Carlo dropout, retraining dropout during inference for uncertainty estimation. After defining the class, we incorporate it into a simple model with a dense layer and compile the model. When reviewing the code, note how the dropout is applied conditionally based on training mode. Third, custom normalization max norm dense. Next, we create a custom dense layer called max norm dense. This layer applies a max norm constraint to its weight matrix each time the layer is called, clipping the weight values to a specified maximum norm. We explain the build method where the weights are created, and then in the call method, we use TF clip by norm method to ensure the weights do not exceed the set threshold. Finally, we build a small model using this layer and review its summary. Fourth, TensorBoard integration. TensorBoard is used again here now in the context of more advanced model setting. We simply set a new logging directory for advanced training experiments, instantiate the TensorBoard callback, and explain that it should be added to the training callbacks. This is very similar to our earlier TensorBoard setup, but demonstrate that these best practices apply at every level of model design. Fifth, custom loss function. We implement a custom Uber loss function. The custom loss class custom Uber loss inherits from Keras losses loss and defines its own call method. The Uber loss is less sensitive to outliers compared to mean squared error. We define how the loss is computed using a quadratic term for small errors and a linear term for large errors based on a delta threshold. Finally, we note how to instantiate and use this loss in a model. Sixth, custom activation, initializer, regularizer, and constraint. We demonstrate how we can create our own custom components, that is, a custom activation function that implements a variant of leaky relu, a custom initializer that is similar to blow a custom L1 regularizer, and a custom constraint class that forces weight to remain positive. After defining these custom functions classes, we build a dense layer that incorporates them. This is a powerful technique to have more control over the model's weights and activations. Seventh, custom metric. Uber metric. We implement a custom metric called Uber metric. This metric computes a Uber-like error measures over prediction similar to our custom loss. We subclass the Keras metric class and override the key methods update state result and reset states. This is useful for monitoring and training performance with metrics tailored to our application. Part 8, custom layers example. We explore by building multiple custom layers. First, exponential layer applies an exponential transformation. MyDense is a custom implementation of a fully connected layer. Add Gaussian noise adds noise during training to simulate data augmentation or improve robustness. We also use the built-in layer normalization. These layers are then combined into sequential model that is compiled and summarized. This segment illustrates the flexibility of TensorFlow's layer API allowing you to create entirely new behaviors. Ninth, custom model residual regressor and residual block. This segment focuses on building a custom model with residual connections. We start with a residual block that contains two dense layers. The block adds the input to the output of these layers to create a shortcut connection. That is the key idea behind ResNet architectures. We then define residual regressor which stacks two such blocks and finishes with an output layer. There are two ways to ensure the dimensions match, adjusting the input shape or incorporating a projection. Here our code shows the basic approach and we can enhance it later to include a projection if the shape differs. 10, custom optimizer, my momentum optimizer. We implement a very simple custom optimizer. This custom optimizer subclass is Keras optimizer class and provides a custom apply grading method that illustrates how gradients can be manually applied. Although the implementation here is rudimentary, and for demonstration it shows how we can create our own optimizer by overriding core TensorFlow functions. 11th, custom training loop for fashion means example. Finally, we show how to write a custom training loop using fashion means dataset as an example. We first load and preprocess the dataset by flattening and normalizing the images. We then create a simple sequential model and define the loss function and optimizer. Instead of using model fit method, we write a loop that iterates over the dataset patches. Inside the loop, we use gradient tape to compute and apply gradients. This gives us full control over the training process, which is useful for custom training behavior, debugging, or when using models that require more dynamic updates. This video covered an in-depth guide covering a wide range of techniques from data augmentation to advanced model customization with Keras and TensorFlow and helps us to gain a deeper understanding of each method and experiment with our own models.